My name is Peter Saraga. I'm Vice President and International Secretary of the Royal Academy of Engineering. On behalf of the Academy, it gives me really very great pleasure to welcome you here for the annual Lloyd's Register Educational Trust Lecture. Before I have to go, of course, through the housekeeping rules, but before I was going to say, this is quite a nostalgic experience for me because this is my very first lecture that I ever gave. Public lecture was in this room, standing just here, so it was many, many years ago. But it was almost exactly as it is now. So tonight's lecture brings together several strands of particular interest within the Academy. Firstly, the engineering response to climate change and energy is one of our key priority topics under the leadership of our President, Lord Browne. Tonight we will hear more of the underlying scientific rationale for taking the subject so seriously. The next theme that is important to us is understanding the nature of risk and prioritising responses to best effect. That's something that has occupied us in many fields, typical of which has been our work on nanotechnology. Finally, the issue of focusing research to inform wise decision-making, I'm sure, needs no justification before this audience. And all this is essentially a preface to my extending a very warm welcome to tonight's speaker, Dr. Richard Spinrad. He's Assistant Administrator, the Office of Oceanic and Atmospheric Research at the United States National Oceanic Atmospheric Administration. Dr. Spinrad will share with us his insights into understanding society's impact on the oceans and the ocean's impact on society. We'll also learn how oceanic and atmospheric research has extraordinary implications for risk-informed decision-making from a local to a global scale. I'm quite sure that his speech will be highly stimulating. Dr. Spinrad has had very broad experience in marine science, technology, operations and policy at the highest levels. During his career, he has worked in a wide range of positions in government, academia, industry and non-governmental organisations. His academic background was in marine geology and physical oceanography. He's been president of a company developing oceanographic sensors, and he's managed oceanographic research at the Office of Naval Research. Among many roles, he has served as the US Permanent Representative to the Intergovernmental Oceanographic Commission of UNESCO and co-chairs the White House Joint Subcommittee on Ocean Science and Technology. He's also president of the Oceanography Society. The fact that he has spent a year of his life at sea conducting research tells us there's a man who really knows the oceans at first hand. Now, this is the 16th year of our Lloyd's Register Educational Trust Lecture. The Academy is very grateful for the continued and generous support of Lloyd's Register Educational Trust. And without the Trust's support, this lecture series couldn't happen. And I'm delighted that Lloyd's Register Educational Trust, 12 months ago, agreed to support the lecture series for a further 3 years. And I'd particularly like to thank and welcome, therefore, Mr. David Morehouse, the Trust Chairman, and his Director, Michael Franklin, who's sitting in the front row. And they've been the driving force behind this lecture series. And I'd also like to thank the other directors and managers of the Trust for helping to make this event happen. The Academy is enormously grateful to you all. And I'd like to invite Michael Franklin just to say a few words about the LRET. Michael.
Thank you, Peter. Dr. Spinrad, distinguished guests, welcome from the Lloyd's Register Educational Trust to this prestigious annual lecture. I don't want to delay the exciting part of the evening very long, but I did want to just take a short opportunity of explaining a little bit about the Lloyd's Register Educational Trust. The Trust was formally set up in 2004 by the Lloyd's Register Group, which, as some of you will know, is an independent international risk management organisation, a very venerable organisation that began life in the City of London in 1760. So in 2 short years we'll be celebrating the 250th anniversary of Lloyd's Register. As part of its constitution, Lloyd's Register has charitable obligations, and to summarise the principal one, it's to support engineering education worldwide. And over the years, Lloyd's Register has done that very splendidly in a number of different areas. In 2004, though, it set up the Lloyd's Register Educational Trust as an independent charity with its own board of trustees, of which David Morehouse is the chair, to actually bring a stronger focus to these charitable obligations. And very briefly, the purpose of the Lloyd's Register Educational Trust is to fund advances in transportation, science, engineering, technology, education, training and research worldwide for the benefit of all. The sole benefactor of the Educational Trust is indeed the Lloyd's Register Group, who've been very generous since its establishment and have made a donation to the Educational Trust of £6 million each year. So we've been very fortunate in that respect. Once the group has handed over that money, though, it's then up to the trustees of the Educational Trust to decide how it's used. The group has no direct say in that. The Educational Trust focuses on 4 sectors, and they are pre-university education, which is school children, and most of our commitments at this moment are in the UK in that particular sector, but we're very determined as an international charity to change that and to broaden our base. The next sector is called university education, where we fund scholarships and awards, again around the world, in all aspects of engineering. What we do there is we fund universities and similar academic institutions who are able to run those schemes on our behalf. Our third sector we call vocational training and professional development. And what we're doing there, obviously, again, through suitable organisations, is supporting individuals who wish to raise their skills or develop their skills. And finally, and most importantly, in terms of the allocation of money, we have a research sector. And here we fund centres of excellence around the world who will do fundamental research into transportation science, engineering and technology issues and work across a range of industries. The majority of our centres at this point in time focus on the shipping industry, but in the last 12 months we've broadened that out deliberately, and we're now supporting a chair in nuclear engineering and decommissioning at Lancaster University, to name but one, and a chair in railway engineering at Delft University of Technology in the Netherlands. So 4 sectors. We have very exciting times. We have something of the order of £15 million worth of commitments that stretch over the next 3 to 5 years. And the last thing I'd like to say is you hear the name Lloyd's almost every day, and I just wanted to emphasise that the Lloyd's Register Group and its Educational Trust are quite separate from the insurance market, Lloyd's of London, or indeed the bank. And on that note, I'll hand back to Peter.
Thank you, Mike. Well, we now come on to the main part of the evening, the lecture. Dr. Spinrad has agreed to answer questions afterwards, but now, without further delay, it gives me great pleasure to welcome him to give us his address on risk-informed investments in oceanic and atmospheric research. Richard.
Thank you, Peter and Michael, for that very warm welcome. It really is an honor to be here tonight. Let me start by recognizing the distinguished members of the Academy, our honored guests, many of my colleagues whom I've known for many years, ladies and gentlemen, and especially let me thank the Trust and the Academy for this a true honor, a very special occasion. I understand that from my preliminary discussions, I am in fact the first American to come here for the delivering this talk, which I interpret to mean that either you have lowered your standards or you're raising your sympathies, one or the other. I look forward very much to representing my government and my community's interests in what I'm about to talk about. And what I am going to talk about is effectively uncertainty and consequence, issues that affect what we do in oceanographic research, issues that are at the heart of engineering concerns. And my intent tonight will be to stand before you and talk about how we take these considerations, arguably somewhat subjective in nature, use them in making decisions associated with research priorities specifically in the environmental field. And by way of setting the stage, it's perhaps important, especially with an audience like this, to talk about the very nature of the kinds of issues that are affected by the research that we are developing. And these are natural disasters. These are the events that happen around the world, but they seem to be happening with some increased impact. Now, I didn't say increased frequency. What I said was increased impact. And the reasons for that are manifold. Everything from coastal development increasing to costs of development. But what we have seen over the last several years is that In the last 10 years, these kinds of natural disasters, as shown here, from 1975 to 2005, with estimated damages shown in constant U.S. billions of dollars going from zero up to $220 billion, that the world has suffered damages in which more than 2.5 billion people were affected, almost 500,000 were killed, and economic losses over this period of nearly $700 billion. Notably, some specific events, the Kobe earthquake back in '95 and Hurricane Katrina, which had impacts now going over $100 billion, skew this particular curve. But even when you take those particular events out, you can see there is a general tendency to increase. So, what I'd like to do is give you some sense by way of introduction of what the nature of these kinds of disasters might be. And many of you are familiar with these, but those of you who are not undoubtedly will be impressed by some of the imagery, some of the eye candy, if you will, that I'm going to share with you. This is a satellite image of Hurricane Katrina. What I'd like for you to notice, first of all, is the size of this particular phenomenon. This is an extraordinary storm. Most storms, just by way of perspective, this is the Yucatan Peninsula right here. This is Florida, this Gulf of Mexico here. The extent of this hurricane, as indicated by the cloud patterns, goes from roughly the southern end of the Yucatan Peninsula up here to the Carolinas. It's an extraordinary, extraordinary storm. It reached Category 5 in the classic Saffir-Simpson categorization scheme. Prior to making landfall, it made landfall at a Category 3. But more importantly, and this is something I'd be glad to address in Q&A if you'd like, it's not about what the hurricane category is, it's about the magnitude of impact, the structure, the size. This particular hurricane impacted 93,000 square miles of the U.S. coast. In addition, the hurricane hits, it dissipates or moves out of the area, and the consequences for days are felt. In this particular case, we had storm surges cresting up over 27 feet in some areas. Insurance claims immediately after Katrina amounted to over $40 billion. There were 1.7 million claims. In addition, as you'll see in a subsequent slide, 75% of the Gulf's 819 manned oil platforms were evacuated. By some arguments, even 2 days before the hurricane hit, the hurricane had already caused the oil industry within the Gulf of Mexico to reduce production by more than a third. So by any measure, lives lost, insurance claims put in, impact on the economic sector, this was an extraordinary storm. Some of the other impacts are shown in images like this. And what you're seeing here is the U.S. Army Corps of Engineers flood status zones, where the zones are characterized by the depth of flooding in feet, from 0 up to greater than 20 feet. So the greens and blues are classically more than 6 feet of flooding. This is the infamous lower Ninth Ward of New Orleans. This is the Mississippi River here. Those of you who've been to New Orleans, this is the French Quarter. This is Lake Pontchartrain. What you're seeing is a lot of green, some blue and purple in some of these areas. Extraordinary amounts of flooding, many days after the hurricane hit, almost a week after the hurricane hit. The disappointing factor with respect to Hurricane Katrina, I can tell you as a U.S. citizen, is that even now in the Ninth Ward, please notice the dates, just 3 months ago, we still see these kinds of remaining effects. A lot of claims have not been filed, a lot of property still remains damaged. We see the remaining consequences of the damage. Interestingly, it may be a bit difficult to see. This is the levee that protects New Orleans from the Mississippi River. Now, if you've been to Mississippi, you know this. Those of you who have not, the river level is above this area here. So all of the homes, and I neglected to point that out, these were homes here. In this slide, the previous slide, home was here. This was the steps up to the home. This is the foundation of some of those homes. The river is clearly above that level. And the slightly lighter shade here is where the levee was repaired, which gives you some extent of the damage to that particular levee. Imagine that as being absent. That's where the break in that particular levee occurred. Home was here. This was the steps up to the home. This is the foundation of some of those homes. The river is clearly above that level. And the slightly lighter shade here is where the levee was repaired, which gives you some extent of the damage to that particular levee. Imagine that as being absent. That's where the break in that particular levee occurred. The nature of the impact is made a bit more personal when you start to look at some of the gruesome reminders. You know that a natural hazard has become particularly egregious when we have to develop a whole new symbology to define what's going on. And in fact, many of you may have seen that as houses were inspected, they were identified by this kind of a symbol where the date of inspection, it's hard to see, but this says 10/9, so October 9th. The nature of the inspection, no entry, meaning they just looked through windows. And then what you'll see down here, and this is the disturbing and awe-inspiring figure, is the number of dead bodies that were seen, detected, or recovered, in this case seen in this particular place. But it wasn't just the people. The Fort Worth Society for the Protection of Cruelty to Animals came in and found 2 pets, 2 dogs that were also killed. So needless to say that the effect just on the people, on their income, went far beyond their own lives and their own property. The quality of life was degraded considerably. And as I indicated earlier, the consequences to the oil sector were dramatic. This is the Thunder Horse platform. That is the consequence of Katrina. This, incidentally, is one of the better cases because they knew where this platform was. In quite a few of the cases, the platforms simply disappeared into the Gulf. Many of them are still lying on the bottom of the Gulf. This is an interesting story unto itself, and one that I'll allude to a little bit more later in the talk. What you're seeing here is a characterization of the track of Hurricane Katrina, identical in each of these cases. The color coding tells you what the category is. Remember I told you about the Saffir-Simpson scale, which is a way of characterizing hurricanes by their peak wind speeds. And so it starts out as basically as a tropical storm, develops into a Category 1, and then by the time it gets here to this part of the Gulf, it is a Category 5, as you can see by the red dot. Then it diminishes, and by the time it makes landfall, it's a Category 3. Now, the sidebar interesting point on this, and one which I'll emphasize a bit more with respect to the research needs, is historically, people have said you look for the warm spots in the ocean, and that's where you tell how the hurricanes are going to intensify. This is the image of the reds and yellows and oranges is the sea surface temperature in the Gulf of Mexico. From that, you could never conclude where this particular hurricane would intensify. There is no rhyme or reason as to why the hurricane intensified in this particular area. It's not until you start looking at the full water column, the heat content of the full water column, and then what you start to see, and that's what this chart depicts, is that this area right here is the area where there was an extraordinary amount of heat, that is to say energy, in the full water column, and that's why the hurricane intensified there. I'll talk a little bit more about that in a minute. Now let's take a look at another kind of natural disaster. And this is the Boxing Day tsunami, 2004 in the Indian Ocean. Very different kind of natural disaster. The statistics on this one are equally daunting. 274,000 people were killed, 500,000 are homeless, and to this day, many people lost their lifestyle, the ability to make money, to make a living. The fisheries were destroyed in many places. Even if you were able to go fishing, there was no land-based infrastructure to take your catch, process it, pay you for it, and transport it out elsewhere in the world. Now, what you're seeing here is an indication of the wave amplitude from the tsunami, which of course started just off Indonesia here. The wave amplitude is shown in centimeters here, 250 down to 0. And the point of this is, no surprise, the major impact here, especially in the eastern Indian Ocean, but a couple of things jump out at you. First of all, it is a global phenomenon. And I'll show you a movie in a few minutes to demonstrate that the tsunami itself was detected throughout the world. We had tide gauges on the west coast of the United States that picked up the tsunami. Now, granted, it was in the 1 to 3 centimeter range, but it was still detected. The other point to notice in this is it's not like a pebble in the bathtub. The pebble in the bathtub radiates in a nice spherical wave. That's not what happens here. So the very science of forecasting how a tsunami will propagate, why is it that Sri Lanka was hit so hard? But in fact, very little happened down here in Australia. Why is it that there are these rays of high-level tsunami effects in some spots but not in others? Fascinating question. Global in nature, local in impact. Local impacts are shown here on this slide and the next one. Banda Aceh, on that corner of Sumatra, right up here in Indonesia, suffered considerably. And many of you saw the images that were on the news. This is a before and an after shot of one area of Banda Aceh. You can see bridges out, roads out, major pieces of land reclaimed by the sea. Remember, this is now 3 days later. This is not instantaneously as the tsunami is hitting. Permanently damaged, permanently destroyed. Another area, similar kinds of things. And even if the land is not reclaimed by the sea, in many cases it's so badly eroded that it can no longer be used for the kinds of functions it was used for before. Some images of when the tsunami hit, and just in many respects like the hurricane, people tend to think, well, it's a big wave that comes in, does most of the damage. It's a sustained effect over many hours. When you've got surges of tens of meters coming through villages like this, basically wipes them out. The power associated with the tsunami is phenomenal. Now, I was fortunate to be in Banda Aceh back in September, and I took a couple of shots I wanted to share with you to demonstrate a couple of points about the power, if you will. In this case, I would argue, since we are here at the invitation of the Royal Academy of Engineering, I'm going to be very careful about my terminology. What this really demonstrates to you is the force. This is a mosque, and you'll see the force of that particular tsunami was enough to break this pillar, and you can see breaks in some of the other pillars. You want to talk about work, that is force times distance. Take a look at this shot. This is a power generation barge. In this part of Indonesia, prior to the tsunami, they used barges that were moored offshore, typically 3 or 4 kilometers offshore, diesel generator barges to send power to the villages onshore. This one is no longer offshore, and in fact, it is 5 kilometers inland. That's a lot of force to move something that far. So hopefully what I've done in these first few minutes is share with you something about the magnitude and impact of a couple of classic kinds of natural hazards. And what I'd like to do now is discuss some of the aspects of risk assessment, some of the risk communication issues we've got to deal with, and then get to that nugget of uncertainty and consequence. And the real challenge to us as researchers comes down to our ability to forecast these phenomena. The accuracy of forecast spatially and in time is the fundamental challenge. The key focus then, I'd like to read from you a statement that I included in the paper. The key focus of the talk is that the fundamental questions are whether research into these and other environmental phenomena may help reduce what are clearly significant risks associated with the forecasting of natural hazards and how such risk implications might be used to prioritize oceanographic and atmospheric research investments. That's the real kicker. If we had unlimited research resources, we wouldn't have to prioritize. But we do have limits. We all have limits, whether we're in the private sector or the public sector. So we've got to start developing some concepts, some decision aids for how to take these limited resources and apply them to get the most benefit to improving the forecast of some of these kinds of natural hazards. So a concept is proposed. And the concept is one for assessing risk of the global impact of different kinds of natural hazards, natural phenomena. Now, I can't overemphasize the fact that we're talking about the global impact here, because obviously, for the people of Banda Aceh, their concern about the hazard of tsunami far outweighs the concern they may have about hurricanes, for example. So keep in mind that global means both in terms of the spatial extent, which is why I showed you that image of the tsunami propagating around the world, but it also is in terms of time. Remember that first slide I showed that showed the increasing consequence of natural hazards. And over time, when one looks at something like the earthquakes, the Kobe earthquake, because that doesn't happen every year or every other year, over time, that tends not to be as impactful, I would argue, as some other factors. So what we've got here is 4 examples of natural hazards that I'd like to dwell on a bit more in my talk and try to convince you on how we can assess how to spend our resources based on a risk and consequence and uncertainty type analysis. So along this axis here you see the hazard, the global hazard. Either it's low or it's high. And on this axis you see the consequence being the exposure times the value. Now the value proposition can be a very personal one. For example, I was born and raised in New York. I consider myself a rather adept jaywalker on the other side of the pond. My exposure and the value proposition is a lot higher when I come over here to London because I keep looking to the left as I start to jaywalk. So my behavior hasn't really changed, but I would argue the value proposition has changed. Depends on personal situations. It depends on specific circumstances. So what I'm presenting is somewhat simplistic, but I want you to think in a grand integrative fashion. And when you think that way, I would argue the hazards and the consequences are extraordinary when we look at climate change. And I'll make that argument a little bit more in subsequent slides. I would argue, by the same token, the hazards are relatively low and the consequences globally are relatively low from red tides, harmful algal blooms. For those of you who are not familiar with that concept, I'll explain it in a slide or two a little bit more. So I want you to gather that concept, but I also want to point out one other aspect of this particular slide. The way these icons are drawn is by design. Some are larger, some are smaller. That's the uncertainty factor. Right now, there is considerable uncertainty with respect to the projections from climate change. Let me show you what I mean. This is the set of projections of surface temperature change as published in the Intergovernmental Panel on Climate Change. All of our governments signed off to the IPCC Fourth Assessment Report that came out last year. And in that, they've done some very clever things. They've said, look, we don't know what's going to happen to carbon dioxide concentrations in the future. It's driven by a number of factors: policy, technology, personal practice. Incidentally, I was absolutely stunned on my flight over here this morning on Virgin Atlantic to see that they will now accept donations for carbon offsets based on your flights. Now, the part I couldn't quite understand was why the people in economy wouldn't pay as much as the people in upper class for a carbon offset on the same flight. If someone can explain that to me in the Q&A, I'd appreciate it. But we've gotten to an interesting point where people are now recognizing that there are things that we will need to do with respect to carbon dioxide. But I digress. The point here is that the IPCC said, let's take a couple of scenarios. We'll call one B1. We'll call one, for reasons that we don't need to go into, A1B, and we'll call one A2. And you can imagine these are scenarios such as, let's double CO2, or let's stop the emission of CO2, or let's draw down to 1990 levels. Those kinds of scenarios. The next question is, what do our models say will happen in the years 2020 to 2029, roughly 2 decades from now? And what do our models say will happen in 2090 to 2099, the end of this century? Now, each of these blocks shows the same information as these two. So, for example, this slide shows that in the B1 scenario, we can expect in 2 decades the surface temperature in the globe will increase by about 1 degree, and by the end of the century, it will increase by 2 to 3 degrees. In this scenario, it says we will have higher increases. Each of these blocks shows the same information as these two. So for example, this slide shows that in the B1 scenario, we can expect in 2 decades the surface temperature in the globe will increase by about 1 degree, and by the end of the century, it will increase by 2 to 3 degrees. In this scenario, it says we will have higher increases. But what you also see is the uncertainty. And where you see it is in the many different projections shown here. So we have a couple of different kinds of uncertainties. We have uncertainties with respect to the process, and we have uncertainties with respect to the product. What we're looking at here is the uncertainty with respect to the product. If we run a certain carbon dioxide scenario, what do we predict the temperature change will be? Now run it again with a different model. There are 20 or 30 models out there with slightly different physics. One treats clouds differently from another. One treats ocean circulation differently from another. One treats soot and carbon particles differently from another. So run all of these and then build an ensemble. And the point is, no matter how you do it, we can see that under each of these scenarios, the Earth will become warmer. The question is, by how much? That's why, in this slide, this particular symbol is so large. Now let me talk about tsunamis. Now in this case, the forecasting capability is pretty good. Now when I say that, I should qualify it. I can't tell you that there's going to be a tsunami a week and a half from now in the Pacific Ocean. But when I talk about the goodness of that forecast, I can tell you that as soon as we have a tsunami-generating event, an earthquake, a mudslide, our ability to predict where and when that tsunami will hit. Remember that earlier slide that showed it's not just a clear bubble spreading out? Our ability to predict that is pretty good. So I would argue the uncertainty is relatively low. And in fact, as a demonstration of that, I'd like you to see this. This is a simulation of the 26th December 2004 tsunami. Remember I told you it was a global event? Well, that's what you're seeing. You're seeing that it extended all the way around the world. Now, this is a model simulation done by scientists from the Pacific Marine Environmental Lab in Seattle, Washington, but it's been validated with observations from tide gauges around the world. So if I run it again, we can take tide gauges in Australia, time when that wave hits. We can have tide gauges over here in Brazil and find out when it hits now and what the magnitude of that was. So in timing and in magnitude, the models work pretty well. The uncertainty is relatively low with respect to tsunami forecasts. I would argue that the hazard globally is moderate. Moderate. Certainly compared to climate change, it's moderate. And the consequences are relatively low. Now, that's an awful thing to say to the people to Indonesia and Sri Lanka. But recall that first slide, the first slide that showed the cumulative damages in billions of dollars. You did not see the Indian Ocean tsunami on there. It was 2004. It was embedded in that curve. The point is that even though there has been extraordinary damage from the tsunami, globally, the numbers are significantly lower than what we have seen from tropical cyclones and tropical storms. Let's talk about tropical cyclones and tropical storms. In this case, I would argue that there's a bit more uncertainty, and I'll explain where that's coming from. The hazard's probably about the same, but the consequences tend to be larger because globally, there are more people that are affected. Remember, the hurricanes happen all over the tropical and temperate world. You're just seeing the Atlantic here, but there is a Pacific equivalent from the typhoon tracks. This is 150 years of hurricane tracks in the Atlantic. And the point, of course, is we tend to think of the impacts on places like the U.S. Gulf Coast, but I'd remind you, somewhere back in history, there's at least 1, 2, 3 that came over this island. So they are somewhat global. Of course, the damage tends to be localized to this particular area, but it's a large area that's affected, and you can see it's many hundreds of hurricanes that have hit. It's probably close to 1,000 tracks in this particular slide. So it does have global implications. Now, the last natural hazard that I included here is red tides. And there's high uncertainty with respect to the forecast of red tides, and I'll explain that in a minute. But because we're dealing with a global issue, it's a very localized phenomenon. The consequences tend to be relatively low. These consequences can be minimized once we've improved the forecast capability. But I'm showing you an example. This is a best case scenario of how we can forecast these. This is the only example that you will see in the world of an operational forecast system for a harmful algal bloom. Now, these are red tides. These are these awful organisms through a variety of insidious mechanisms that can cause paralysis, they can cause awful respiratory problems, they can cause amnesia, depending on whether they are eaten, depending on whether the vapors that they emit are actually breathed in. And in this particular case, off the Florida coast on the west, there is a species of organism called Karenia brevis, or K. brevis. And we have learned that we can use satellites to detect K. brevis and only K. brevis. So we've found a way to isolate that species early in its production, as a bloom is developing. And we can ignore all of the other species. When we do that, we get images like this. The red are higher concentrations of these organisms. And then, using a variety of observational techniques, we have buoys offshore that tell us what the winds look like. We know pretty well how these organisms multiply and grow. We can predict that in 2 or 3 days, you can expect, based on the wind patterns, that the hospitals in this area, and this is near Tampa and St. Petersburg, Florida, will see increased admittance of respiratory problems, because this particular organism actually gives off gases that cause problems for people with asthma and other respiratory diseases. So we can generate this kind of a harmful algal bloom bulletin. But recall now that I said that the uncertainty was relatively large here, yet I've just shown you an example of where we can forecast well. Well, as I said, this is the only place we can forecast well. There are harmful algal blooms in coastal waters all around the world. We have not developed the kind of specificity of observations, and we don't understand the physiology of these organisms well enough that we have this kind of accuracy of forecast everywhere in the world. Best evidence I can give you is within a year of developing this forecast system, we had a major bloom off Cape Cod in the United States of a different organism. We couldn't forecast it. It just about shut down the shellfish industry in the northeast United States with extraordinary economic consequences. So now we've been talking about hazards versus consequence. What I'd like to do is translate that now to include the uncertainty component. Let's apply what we know about uncertainty to develop a decision aid. And this is the first formulation of that kind of decision aid. Recall that the goal of this exercise is to develop research priorities. I got a pot of money. I'm going to invest it in research. Where should I invest it for the best impact, the best bang for the buck? Well, obviously, that area where you have highest uncertainty and where the risks, defined as the probability times that consequence, are highest. If you're in this sector, you should have high payoff for your investment. I would then argue that what you really want to do is lower the risk as much as you can. And so I would invest in those areas where you have with increased research investment, you've got reduced uncertainty. You may not do a lot for the risk, but at least you've made that bubble smaller. Then you want to go to where you can reduce uncertainty in the low-risk area. And then finally, and I would argue this is the area you don't tend to want to put a lot of research dollars in, where the certainty, if you will, is high, that is, the uncertainty is low, and the risk is already relatively low. You're foolish to spend research dollars in that area. So let's apply this decision aid of uncertainty against risk to the 4 specific natural hazards I described. Now, this is overly simple. I'll be the first to tell you that. It also suffers from that regional and specific concern. When I go talk to the Indonesian government about research investment, I won't tell them that they should not invest in tsunamis. Obviously, this has specificity that each individual investor has to apply. But for an agency like my own, the National Oceanic and Atmospheric Administration, which has mission responsibilities in all of these areas, how can I prioritize where to put those bucks? First place, where we should put the dollars, is up in the climate change arena. The climate change arena, where we are going to see, with increased investment, a reduction in uncertainty and hopefully some reduction in risk. I would argue that we want to go to hurricanes, then red tide, and then tsunami, in that order. Now, part of the issue in addressing this kind of decision aid is how you communicate risk. I've tried here very quickly and simply to communicate risk in certain ways. There are people a lot better than myself, many of them in the audience, many of them who have had great success in conveying to the public the risk of investing or not investing. And I would be remiss, especially with an audience like this, in not directly quoting from the Stern Review on the issue of risk and investment, where in the Stern Review report, one conclusion was that using the results from formal economic models, the review estimates that if we don't act, the overall costs and risks of climate change will be equivalent to losing at least 5% of global GDP each year, now and forever. If a wider range of risks and impacts is taken into account, the estimates of damage could rise to 20% of GDP or more. That was a clarion call to the world with respect to climate change. There have been several others. One which just recently came out looks like this. Let me explain what we're looking at here. This is a portrayal of what would happen in climate with a doubling of carbon dioxide. And there's a number of things you can look at when you say what would happen in climate. You could look at ocean temperatures at the bottom. You could look at ocean pH. You could look at atmospheric temperatures at a certain level. In this case, we're looking at continental temperatures. On this axis, you see in temperature from 0 to 15 degrees Celsius. And in this axis, it's cumulative probability. So we have a probability distribution function here. Now, the probability distribution function captures some of the uncertainty I showed in one of the earlier slides, because what it says is, based on all of the models that have been run, we have a mean of projection that we will see a 5.5 degree centigrade increase. Now, I have to pause here for a minute and ask 2 questions of the audience. Do any of you have fire insurance in your homes? I see a show of hands. Okay. Do any of you play Russian roulette as a matter of course on a regular basis? A colleague of mine, Jim Hansen, would argue that you're fools if you do either one of those things. And the argument goes, and I have fire insurance myself, so I freely admit that I'm a fool. The argument is that when you look at the probability and the consequences, it's such extraordinarily low for fire to your home that the dollars that you spend cumulatively over years should be better spent on investments rather than on fire insurance. More importantly, when you apply the Russian roulette example to this particular curve, remember, Russian roulette, you have a probability of 17% that you will get shot. And the consequences are irrefutable when you get shot. When you look at this, I would argue that when you start getting up over 10 degrees centigrade continental temperatures, the consequences are irrefutable. I would argue they are drastic. I would argue that life and lifestyles as we know them would cease. Just by way of one example, if you look at the agricultural consequences of that kind of shift, there would be a poleward shift in the agricultural belts. However, most of the northern latitudes cannot sustain that kind of agriculture because of the soil content and chemistry. And consequently, if you think we've got a food crisis now globally, it would be blown way out of proportion. Water availability, water quality, any number of factors, sea level rise. When you start getting into this area, you are now facing extraordinary consequences. And consequently, if you think we've got a food crisis now globally, it would be blown way out of proportion. Water availability, water quality, any number of factors, sea level rise. When you start getting into this area, you are now facing extraordinary consequences. How do we communicate that? How do we convey this probability function in terms of the consequences here? If this scale went from 0 to 1 degree, we wouldn't really need to worry too much. But it goes from 0 to 15 degrees. That's an extraordinary impact and one that we need to consider. How do we work with something like this? Well, the first thing is move this curve to the left. Reduce the uncertainty. That's what this curve is showing you. It's the uncertainty of the forecast. How do you reduce the uncertainty? Well, that's where the research comes in. Another example of communicating uncertainty, one of my favorites. This is the forecast, the official forecast that was provided at 11 p.m. on Friday for Hurricane Katrina. When our National Weather Service, part of my organization, puts out these forecasts, we put them out with 24-hour prediction, 48-hour prediction, 72-hour prediction. So at 11 p.m. on Friday, we predicted that this hurricane would hit the coast around 8 p.m. on Monday. What you're seeing there in the red dot is where landfall occurred. Now, the cone of uncertainty that you see here is based on the historical nature of these kinds of hurricanes. It's 100 miles on a side, and we basically plunk that cone down there. There's an uncertainty. There's a distribution of probabilities around that. When you nail a forecast like this, it really doesn't matter what that cone of uncertainty looks like. But a week later, we had Hurricane Rita. And this is what the forecast for Hurricane Rita looked like. Same context. 24, 48, 72-hour forecast. This is where Rita made landfall. Many of you may have seen the news about the unnecessary evacuations that were conducted out of Houston. Rule of thumb, $1 million a mile. When you have to evacuate a coastal area, it costs about $1 million a mile. So if you evacuate the wrong coastal area, as was done here, you're spending a lot of money and frustrating a lot of people and losing credibility. You're not communicating uncertainty well. Now, we would argue, wait a minute, we showed you what the cone of uncertainty was. Look at that. It's right in the cone of uncertainty. What's your problem? I know for a fact when I went down and talked to people there, I had one family tell me that they looked at this. They sat around the table, the family dining room table, and decided based on this chart, since they lived right around there, that the black line wasn't going to hit them. They were going to stay home. Which told me they had more credibility in discussing this with Snuffy the cat than they did with the forecasters at the National Weather Service. So how do you communicate this kind of uncertainty? This is a product we have developed. We're trying to use this to convey uncertainty using probabilistic forecasts. The interesting thing here is where social sciences comes in. There is not a weather forecaster around who wants to use probabilistic forecasts. The weather forecasters want to tell you it's going to rain tonight. And the reason they want to do that is because their broadcast managers don't want them saying there's a 70% chance of rain tonight, because you're going to change the channel and go look at somebody else's forecast. So how can we take a forecast and use some kind of color coding that says, you know, the purple is really bad, we're really sure there's going to be a problem there. And when you get out in the yellows and greens, yeah, you ought to be ready. You ought to be buying some plywood. You ought to be gassing up the car, getting ready to evacuate. It's a very difficult problem. We have not succeeded in conveying and communicating uncertainty well. So that's part of the research necessity, I would argue, is the social science associated with reducing the concern or frustration or lack of awareness on the part of the user community with respect to what the risks are. But we need to develop that investment portfolio. We need to take account of all of this, apply it towards research activities in a way that can reduce the uncertainty and minimize the consequences. And I want to spend just a couple of minutes giving you some examples that are specific to the kinds of things we talked about. But I have to give you a caveat, too. Wouldn't it be great if research managers like myself could simply say, look, we've done an analysis, we've got a quantitative assessment of risk, uncertainty, we've looked at ensemble forecasts, we know how many people are going to get killed, we know how many miles we have to evacuate, here's how we want to manage this. Doesn't work that way. What we also have is all of this doctrine, and what you see here in this virtually unreadable slide is just a snippet of the laws, policies, programs that are dictated, in this case, by our administration and our Congress, that tell us how to spend money on tsunamis, how to spend money on harmful algal blooms, how to spend money on hurricanes, how to spend money on fisheries. I just bring that up mostly to gain your sympathy for the troubles we have in doing our job, but also to point out it's not quite as simple as having this kind of diagram that says, let's just look at the exciting research and tie it to the risk analysis that I described and associate it with the missions that I said are relevant. So what I've tried to do here is give you a sense, using the same quadrants you saw on a previous slide, of the kinds of things we're doing for hurricanes, tsunamis, climate change, and harmful algal blooms. We have three criteria we apply to our research. The first is it's got to be relevant to the mission. So, for example, one of the biggest problems we have with reducing the uncertainty in hurricanes is getting lower level winds. I have yet to find a pilot who's willing to fly a P-3 aircraft 50 meters off the surface of the ocean during a tropical cyclone. But you know what? We could fly an unmanned aircraft, and we have done that. We're now flying unmanned aircraft into tropical cyclones to get those winds. This, incidentally, is an artist's rendition, for those of you who are wondering, how the heck did we get that picture? This is a fascinating concept. Right now, whether it's cap and trade, carbon tax, whatever policy, revisiting Kyoto, whatever policy the global community establishes, we're going to have to monitor and provide global assessments of sources and sinks of carbon dioxide. We only have about 100 observations regularly around the world, so how do we integrate those data, interpolate them, and provide something that people can use to determine whether CO2 is going up or going down? So we've developed something called Carbon Tracker, which is a blend of observations and models to characterize the concentrations, sources, and sinks of carbon dioxide. Autonomous underwater vehicles are not new. Those are basically underwater robots. In fact, go to Southampton, you can see some of the leading technologies associated with autonomous underwater vehicles. But in this case, we've built something called the Brevbuster. Remember Karenia brevis, our old friend, the harmful algal bloom? Now we can go out and monitor it in real time, not just using a satellite, but sending this robotic vehicle around to actually count the numbers of cells and look at them throughout the water column. This slide, which has some imagery associated with it, let's just go ahead and play it so I can talk to it while it's going through. It takes about 2 minutes to go through this. This is about tsunamis. Remember, the issue is relevance here. And what we determined was that tsunami, once it's generated, travels across the ocean. It travels across the ocean at hundreds, if not 1,000 kilometers per hour. And it's only about that tall in the middle of the ocean. Now remember, the ocean is 3 to 4 miles deep out there. So how could we detect that kind of a wave in the middle of the ocean? Why do you want to detect it in the middle of the ocean, you ask? Because if you can detect it in the middle of the ocean, that gives you about 3 to 4 hours of warning time, as opposed to the 10 minutes of warning time that you get just by watching the ocean recede. So we've developed this kind of buoy system that sits on the bottom, detects the wave when it goes by, sends a signal to the satellites. The satellites then send messages back to the Alaska Tsunami Warning Center and the Pacific Tsunami Warning Center. This buoy can stay out in the ocean for years at a time in the deep ocean. As it says, it monitors at sea level, a remarkable technological feat, measuring a wave that tall in 3 to 4 miles of water. Now, the next phase is going to be to take this concept and not wait for it to detect the tsunami, but tell it when you think there's a tsunami coming, because you just got a monitor of an earthquake. Tell it to start detecting. It comes back, says, okay, I'm ready. There goes the wave. Says, yep, you got a tsunami coming here. Same thing goes into effect again. So you can now query this particular system. We have 39 of these buoys out around the Atlantic, and the Pacific, and the Caribbean Ocean right now. This particular technology is being picked up by the Indonesians, the Thais, the Australians. The next metric, the first was relevance, the next one is quality. I won't spend as much time on this particular metric. There are any number of ways of assessing research quality. I would argue when a group of researchers wins the Nobel Peace Prize, that's a pretty good measure of quality. They happen to share it with this other guy, but these are a few of our folks. In fact, these are all NOAA researchers, people that worked for me in our labs. This is our Secretary of Commerce there. That's a good indication of quality. Another interesting indication of quality is this is that tsunami buoy that you saw the cartoon of a moment ago. It's been picked up. It's been patented. We have non-exclusive agreements with companies like SAIC. That's a pretty good measure of quality as well. When the private sector comes in and says, we want that research result, we want to apply it, we want to commercialize that. The third metric, if you will, for our research is performance. And this is the fuzzy one. How do you measure research performance? Well, I would argue that one way is by leading the technology. And in this case, over the next few months, you are going to see some extraordinary results coming out of this ship. She's in the yard right now being refitted. She's a converted naval vessel and will be the world's only dedicated ocean exploration ship. Bob Ballard is leading the development. This vessel will be out all the time, exploring the world's ocean, using unmanned vehicles, reporting back using broadband data communications in real time. The idea is kids around the world in schools, if they've got Internet 2 connectivity, will be able to see what's going on in the bottom of the ocean anytime, anywhere, and will actually be able to manipulate these vehicles. It also means you don't have to have the scientists out at sea, because now when you start seeing exciting things, you've got real-time data access. You can actually have the scientists sitting in a lab on Internet 2 saying, yeah, I know what that is, grab a sample, go get another one. Or we've seen that before, don't worry about it. This will be online starting this summer. Research performance, another way to measure research performance, sustained observations. I can't emphasize that adequately. We struggle every year trying to sustain observations. You all know this curve. Whether you know it or not, you know this curve. It's called the Keeling curve. It is the curve that shows the observations of atmospheric carbon dioxide in parts per million from 1957 to right now. When Keeling started this curve, he struggled to get funding every single year. Thank God he was able to get that funding, because that's the basis for what you now see as the definition of over 380 parts per million carbon dioxide in the atmosphere. And yet we still have to struggle to get funding for that every year. But the sustained investment is one measure of performance. Finally, and these are my last couple of slides, performance is also measured with traditional performance metrics. And I'll show you two slides that emphasize that uncertainty issue associated with hurricanes. What you're seeing here is over the last 3.5 decades, how our forecast error for the track of hurricanes has come down considerably. Each of these lines represents a different forecast. The red one is the 24-hour forecast, which obviously has a smaller error than the 48 or the 72-hour forecast. And in the last few years, we've started building 96 and 120-hour forecasts. The point is that now this 72-hour forecast is as good as the 48-hour forecast was in 1996. That's a pretty good performance metric. Hurricane intensity, that's where the uncertainty is. It's flat. Similar kind of chart showing the forecast error in the year. We have not improved our intensity forecasts very well. So we can tell you where the hurricane's going to hit, but especially if it's a rapidly intensifying hurricane, we're not very good about telling you how that intensity is changing. So, in closing, what I've tried to do is talk about what we do in oceanographic and atmospheric research in 4 specific areas associated with natural hazards. I've tried to convey it in terms of risk assessment, in terms of uncertainty, in terms of consequences. In the end, you have to build a research portfolio. And what you want is that that research portfolio captures all of those factors and builds for you a mechanism where you understand the nature of our globe so that you can provide the right information in that right format for any user at the right time to the right decision makers to make those correct decisions. Thank you very much.
In terms of uncertainty, you showed us those curves of the spread in projections for the temperature rise at the end of the century for a double or whatever. Now, as I understand it, both the IPCC and the results of something like 57,000 runs done on home computers around the world, or in the UK anyway, show that unambiguously that the biggest uncertainty comes from the modelling and the lack of data on particulates and particularly cloud processes. Now, I didn't pick that up in your description of your program. Would you like to tell us about that?
Yeah, I did not specifically reference that. That's a cogent comment, and I agree completely. I would argue that in the last few years, the recognition of the role that clouds play and particulates is a considerable source of error or uncertainty. And in fact, in many cases, because we have not been able to characterize the spatial distribution and nature of those clouds adequately, the models do not resolve them. They cannot then be extended in terms of the impact. So you can, we call it parameterizing. You can say, I can't resolve that cloud, but I'll tell you what. I'll say that we can expect 30% cloud cover under these kinds of conditions. So there's a lot of hand-waving and fuzziness to that. I agree completely. It's a major source of error. Interestingly, one of the other associated sources of error is actually some of the aviation-induced cloud formation. That if we get off the clouds and particulates for a moment, there also is an emerging set of observations that suggests we have not adequately treated abrupt change in climate. And in fact, one of the areas where there is considerable attention being given on the oceanographic side, especially in Southampton and also our laboratory in Princeton, is on the nature of the overturning circulation, especially in the Atlantic. If you saw the movie The Day After Tomorrow, they obviously did not get the science quite right, but they did get right the idea that somehow circulation in the ocean was tied to climate change and that, in fact, there could be more abrupt changes. Not quite the 12 hours that they alluded to, but I would argue that as an oceanographer, I think that issue is perhaps as important as the issue of cloud resolution and particulates that you alluded to.
My name is George. I'm from AT Consultancy, mainly civil and structural engineering consulting. In Dr. Spinner's view, or rather in the organization that he represents, what can be called the primary source of this carbon dioxide that is causing the heating effect? There are a number of theories being expounded. Some attributes it to man-made harms, other one attributes to the solar, and such that the ocean gets heated, it liberates carbon dioxide which is already dissolved in it, and this, the latter one, there is no way we can control. So all these things, does it mean that we can avoid this thing, or it is unavoidable? Thank you.
Thank you. There are a number of aspects to your question. I think one of the benefits of the IPCC Fourth Assessment Report is it's allowed us to move on from the question of whether or not there is anthropogenic influence. And clearly this is an anthropogenic consequence from emissions and a number of other activities. It has local variability. For example, in Indonesia, the issue of deforestation is a considerable factor. In China and in the United States, emissions from a variety of tailpipe emissions, major coal-burning factory emissions are sources. So the first point is that IPCC clarified that this is clearly an anthropogenic influence. The other point is that we have, by some scientists' interpretation, reached a variety of different kinds of tipping points in nature's ability to deal with this. The ocean's ability to absorb the increased CO2, the ability for the atmosphere to dissipate it to a certain extent. The question of how to deal with this is one that's received a lot of attention. I happen to believe that the work of Robert Socolow is particularly relevant, in which he has argued there is a wedge theory, and that is using whatever curve you imagine showing increases in carbon dioxide or increases in temperature. At some point, they have to level off and turn around. No single factor is apt to mitigate that, and consequently, what sets of different factors need to be applied to mitigate. Adaptation is one, moving agricultural sources, rerouting water, that sort of thing. That's one small wedge. Mitigation from technologies, cleaner emissions, that sort of thing, going to hydrogen-based economy, all of these can be added up in terms of wedges. What we need is, if you will, the commitment to define what the respective wedges are and probably have investments in each of those respective wedges. But we need to start right now and not continue to debate whether we need to develop some of those new concepts.
I'm Dougal Goodman. I'm non-executive chairman of a consortium of insurance companies called the Light or Risk Network. So we're very interested in reducing the uncertainty. The IPCC process, which I fully support, has attracted enormous levels of resources, hence the publications. You put tsunamis in the bottom left-hand corner, but surely there is an issue about the limited research that's been possible because the resources are limited. That the Indonesian earthquake, which led to the tsunami, obviously had a very significant impact on human life. But there are concerns about, for example, there's a subterranean volcano called Kigamjeni, just north of Grenada, which there is a concern in the insurance industry that if that erupted, there would be a tsunami which would have a much higher economic impact because it would flood coastal regions around the Gulf of Mexico. Surely the issue is that the tsunami is in your bottom left-hand corner because the science hasn't really been undertaken in the same way that the climate change science has been undertaken.
I would, first of all, let me say that that is a simplistic approach that I've described there. And let's make sure to understand that that's not intended to convey where all of the resources and how all of the resources should be distributed. It's intended to convey where research dollars should be distributed right now. The physics of tsunami generation and propagation is reasonably straightforward. A tsunami is a shallow water wave that behaves well under physical conditions. The way it's generated is reasonably well understood as well. I go back to the gentleman's question about the sources of variability in climate change forecasts. We don't even know what all the variables are that we should put into some of the climate change projections. We do know what those variables are with tsunamis. What we don't tend to do, in my opinion, particularly well on the tsunami side is invest in the awareness raising and capacity building side. It's interesting to note, as you heard in my introduction, I was the U.S. representative to the Intergovernmental Oceanographic Commission. The year before the December 26, 2004 tsunami, we invested in IOC, I'm going to conservatively say, $200,000 to $300,000 for tsunami research. Immediately after the tsunami hit, we invested $7 billion. Most of the scientists said, let's build detection systems, let's build monitoring networks, and at the very end, people said, and oh, by the way, maybe we ought to build some tsunami information systems, maybe we ought to build on some of the cultural awareness that's available around the world. I believe that the investment that needs to be made in tsunami warning systems needs to emphasize more some of the educational components and capacity building components. I think we've done a good job of investing in the research associated with the physical dynamics of tsunamis. Now, most of the research that we're doing right now in tsunamis is in applying models to particular areas. In the United States, for example, we have a program called Tsunami Ready, where your town can be certified as Tsunami Ready if, one, a model specific to your geography has been built and evaluated to the extent it can, and two, you've demonstrated an evacuation plan that can work in the event of a tsunami. That's reasonably straightforward. It's just a matter of crunching through. We know what needs to be done. It's not a lot of additional research that needs to be done in that regard.
Could I just come back briefly?
Please.
That's the oceanographic side is well understood. The issue for the research is the trigger.
Yeah.
Understanding Kikum-Jenny is not an oceanographic problem. It's a geological problem.
Yeah, I don't disagree with that at all. And the geological community is looking at a number of investment areas in tectonics and seismology that could improve some of that. And recognize it's not limited to just earthquakes, it's mudslides. In fact, it's meteorites as well that could be part of that. As I indicated in my comments, the predictability that I'm alluding to in tsunamis is once the tsunamigenic event has taken place, can you predict where it's going to go and what's going to happen to it? So I agree with your point about predicting that tsunami genesis is not part of this investment.
Can I see a hand raised to the back there? Yes.
David Colwood, engineer. At university I studied control theory, and I always remembered that if you have a stable system that goes unstable, it does one of two things. It either moves to another stable state or it goes completely out of control. How long do you think it's going to be before the research will be able to tell us either whether it will go to another stable state and what that state will be, or whether we know it's just going to go out of control and stay unstable for a very long time?
I assume you're talking about climate. Boy, that's a... you know that, not to be glib, but one of the advantages that climate scientists have is that validation and verification happens long after their professional career is over. And so that begs the question of how do you validate these things? Arguably, the stable states that you've alluded to historically would have been in interglacial times or looking at the full geological record. But, and this is a big but, we don't have that additional component of the anthropogenic influence. So we can't go back 400 million years and say, okay, but now put in 385 parts per million of carbon dioxide with the following kind of distribution mechanism. The models are getting good enough. We could do some of that. But again, you can't, you have no validation of what it would have been like 400 million years ago with anthropogenic influence. So what people tend to do is they look at the models going back 150 years, the pre-industrial time, and look to see how well the models simulate what's happened. Now, what you're really asking is, as you run these models, and in IPCC, I'm going to say that there were about 24 models that were applied across the board. What you're saying is that if you run these enough, will you start to see in the Fourier distribution some modes? A couple of points. First of all, the computational requirements to do that simply are not in hand. We might have them soon. I was in Japan 2 weeks ago. They're talking about a petaflop machine. The Earth simulator used to be the holy grail. Now they're talking about a petaflop machine. So we might be able to run those kinds of simulations. And what I'm getting at is, in order to answer your question, I actually believe we'd need to have very high resolution model simulations run for the globe, arguably 10-kilometer spacing or less, to try to look for those kinds of patterns. And then you'd need to run these models, not tens, not hundreds, probably thousands of times to do that. The second part of my answer to your question is that it has to yield something. There has to be a termination point. And arguably, when you start getting to the right-hand side of that probability distribution function that I showed, some of the controlling factors cease to exist. When that gets up to 20 degrees C, I think it's fair to say that, for example, anthropogenic emissions would go down considerably because most of us wouldn't be here. So arguably, that is a tipping point. You'd reach some metastable state. But what I have not seen is running those models out to the point where they effectively burn out and then see, do they reach an asymptote? Do they just continue to oscillate? I have not seen that, and I think the reason we have not seen that is because the computational requirements are just too demanding right now.
Williamson, University of East Anglia. I'd like to return to the uncertainty.
You may have to press the button.
The problem being that we don't really know what the uncertainty is, and that if the uncertainty is measured by the difference between different models, then it depends what you put into the models in the first place. And that, as an example of that, for the climate models 15 years ago, and they haven't really improved very much because they've become more complicated, because they now include biogeochemistry, they include much more feedback mechanisms, and so that there's far more complexity in them, so that there's far more variability in the outcomes. And as another example for sea level rise, at present the model uncertainty is relatively low because the models do not include an awful lot of factors that might well affect sea level rise, and they might be an order of magnitude out at present for most of the climate models.
I agree with that. I think I would add that it's about more than just the model uncertainty. However, it's also about the observational uncertainty. And what we're seeing right now is that we still haven't converged in terms of what are the optimal observations in terms of frequency, periodicity for many of these kinds of things. The classic example that I face every day in my job is the question of what is our uncertainty with respect to the impact of climate change on hurricane intensity and frequency? It's a raging debate. Even within our own organization, we have both of those arguments. And the reason I bring that up is because part of that uncertainty is in knowing what the observations of hurricanes were in the pre-industrial age. And those observations were limited to what ships at sea tended to report. Well, it's clearly a highly biased observational schema. And how then do you extrapolate that to our modern satellite age where we can see every tropical cyclone that forms? So some of that uncertainty is in the observational limits. The other point is that ocean acidification is an interesting example that people were making some assumptions about where the ocean was going to go biogeochemically as a consequence of warming without considerations of what the geochemistry was of carbon absorption into the sea. Now, with the kinds of observations we've had, where we're seeing in some areas 30% increase, I hate to say increase in acidity, it's really a 30% decrease in the, or 30% change in the pH, because the oceans are not acid, they're basic. But having said that, that observation now has opened up a whole new set of questions about the uncertainty associated with geographic distributions of carbon absorption. So I agree with your comment. I think part of it is also can be addressed through a better handle on observations and observation systems. A related issue in that is if you look at the meteorological community, they have narrowed down much of their uncertainty in forecasts through the application of observing system simulation experiments, where you get this sort of feedback. If I had twice as many drop-sons in this area, would my forecast improve? If my forecast improved, would I put fewer drop-sons out? Of course, I like to point out to my meteorologist friends that all they worry about is pressure, temperature, and humidity, and if they were serious, they'd have ornithologists and entomologists mixed in with them and deal with the kind of problems we have to deal with in oceanography. Having said that, though, they use OSSEs, Observing System Simulation Experiments, to narrow the uncertainty by optimizing the observations. We're not doing that in the oceanographic community. I think the models are good enough. Climate community is starting to do that a little bit more.
There's a question here.
Trevor Guymer, the Interagency Committee on Marine Science and Technology. Further developing some of this and perhaps particularly contrasting the national and regional perspective compared with the global perspective. In terms of sustained observations, I think one can see that with the limited amounts of funding that governments have to put into ocean research and ocean observations, it's going to be the mandatory requirements needed to meet national and regional policies, and in our case the EU, that are really going to drive the funding investments. And the struggle that we have is making the observations in a global perspective. And as you and I well know, the development of the Global Ocean Observing System, we're struggling there because we have only just over 50% of the array that was thought to be needed as a minimal amount in place. And we've plateaued out on that. So my question is, on the basis of a kind of more risk-based assessment, narrowing the uncertainties with research, do you think that we should actually be redefining those goals for the observing system components and using the resources that we think that we're more likely to have in a more intelligent way, so that instead of observing the oceans uniformly, that we actually are much cleverer about this and use that same amount of funding in a completely different way? I'd be interested in your views on that. Thank you.
Short answer is no, I think we're using the resources very intelligently and using them well. By way of answering the question further, I'd like to see a show of hands on who in this audience knows what GOOS is. I'm saying maybe 10 to 15% at most. It's the Global Ocean Observing System that Trevor alluded to, and it is, I would argue, critical to the insurance issues we talked about, the agricultural issues we talked about, the food issue, the water issues we talked about, all of these issues. I would say we're doing a good job with the observations we've got out there. We probably need more of them. What we're doing a horrible job with is conveying the return in something meaningful to the communities that want to see this investment. We're really good at saying, if I put another couple of moorings out, I can get you an improved non-hydrostatic geostrophic model. Would you like that? And, you know, and the glaze factor gets pretty high when you go through that, as opposed to saying, if we put out some more moorings or Argo floats, we can guarantee that we will improve the El Nino La Nina forecast by an additional 3 months, that sort of thing. That's an interesting case, the Tau array in the Pacific and the success that we've had and what the community is now trying to do with the Parada array in the Atlantic. I would argue we ought to be selling that on the basis of these kinds of values to society. We don't tend to do that. We tend to have those dialogues among ourselves at places like the Intergovernmental Oceanographic Commission or the Oceanography Society or the various professional societies. We don't go out and have that dialogue with decision makers, with policy makers, as much as we should. In fact, I've had that discussion, interestingly, with more members of Parliament than I have had with members of the U.S. Congress. So bad on me, I guess.
The one in the middle here.
Yeah, Mike Coffin from the National Oceanography Center, Southampton. I was intrigued by your dedication of one ship to ocean exploration, and I wonder how that ship came to be dedicated to ocean exploration and whether the exploration that it's doing is mission-oriented or is it blue-sky exploration?
My answer to how we got it done is 2 words: Bob Ballard. And I say that somewhat tongue-in-cheek. Some of you know Bob Ballard. He's a very public figure on US TV, involved in ocean exploration. He's as close, I would say, to Jacques Cousteau as we've had in the U.S. community in ages. And he's very aggressive, and he spent a lot of time with Congress convincing them. So the $18 million we got for the conversion came as an earmark to our budget, meaning we didn't ask for it specifically. Congress gave it to us. So in part it was by having a very vocal, visible champion to do this. Back in 2000, there was a presidential commission on ocean exploration that included a number of preeminent ocean scientists: Marcia McNutt, who runs the Monterey Bay Aquarium Research Institute, Sylvia Earle, and others, recommended that there be a program of ocean exploration within the National Oceanic and Atmospheric Administration. You really hit the nail on the head, though, with respect to the mission orientation. We argue that exploration itself is part of the mission. And that because so little is known about the ocean, pick whatever statistic you want, that we've only mapped 5% of it with the same resolution that we've mapped the whole moon, leading to the statement that we know more about the moon's backside than the ocean's bottom. And that exploration itself has to feed all of these other mission areas. How are we going to understand what the resources of the ocean are if we don't explore areas like hydrothermal vents? How can we deal with the consequences of methane hydrate emissions from the ocean under a climate change scenario if we don't even know what the concentrations and locations throughout the globe of methane hydrates are? How can we understand the delicate nature of the ecosystems if, by some estimates, 90% of the species in the ocean are as yet undefined and undescribed? You've got to explore. So we have argued it only works if there's another piece of that, and that is that as you explore and you discover fascinating things, you follow up with the specific hypothesis-based research activities. So it's a bit of a delicate balance. We are trying to codify it by getting our Congress to pass legislation formally authorizing us for that. Until that happens, we'll express it the way I just did. And with gasoline at almost $5 a gallon now, that's going to be a bigger challenge, I think, to keep that ship operating full time.
Right at the back there.
Yes, my name is Gregory Darling of Guardline. We run commercial survey ships, so it's more of a commercial question on funding, which touches on the other comments. What do you think will happen perhaps over the next 5 years in terms of your sort of expenditure, what your government gives you, and what will happen in other parts of the world as well? Because it's a very... the topic is very... it's in every newspaper every day now, so now's the time to strike.
It is in every newspaper. However, if you look at the various surveys, and you said the topic is in the newspapers, there are a variety of topics that show up. I think climate change does tend to show up most of the surveys, but interestingly, in the surveys that we focus on in the States, climate change, first of all, shows up as a separate item of interest from environment, which intrigues me, and second of all, ends up 9th or 10th or 11th. It's on the list, but it's after the economy, Iraq, educational issues, jobs, Social Security, the mortgage crisis, that sort of thing. And now, here's the twist, though. I would argue treating it as such is wrong, because climate change is part of the economy. It's part of the food crisis. It's part of every aspect that is in the top 5 of those, and what we haven't done is convey that. What are the consequences of this uncertainty in terms of whether there are going to be jobs? What are the consequences in terms of where people are going to live? So I'd like to try to, instead of segregating it as a separate issue, blend it in there. I don't think any one of our 3 presidential candidates is going to get elected on the basis of their environmental campaign. And consequently, I believe it's incumbent on us as environmental scientists to convince their respective campaigns that what we do contributes to the things that they consider important. Does that make sense?
Yes, it does make sense, but do you think that there will be an increase in expenditure year on year, 20%, 20%, 30% over the next few years? It's on the agenda.
It's on the agenda. I'm encouraged by what I'm seeing around the globe in terms of attention to these issues. I think that from a research perspective, what's going to happen is in some, there will be increases, but the nature of how we get there will be fundamentally different from how we do it right now. If I use the United States as just one example, for the last 50 years, we've operated on the basis of public funds available for most of this kind of research. And we have rigorously segregated those and isolated them from private funds. In many cases, it's illegal to commingle those kinds of funds. That paradigm has got to change. There's got to be a better way to, for the private sector to identify the appropriate market niches where investment should be made, and the public sector to leverage, co-invest, work with them in that regard. The interesting thing is that we've almost come full circle. If you look at what happened, say, just after World War II, before we got into the mode we're in right now, the way in which public funds were spent to make improvements in certain areas. I worked for the Navy in the United States, so I can talk about the national security improvements. If you look at the way investments were made for national security improvements, by today's standards, acquisition laws are being broken, sole sourcing is violated. That's the way it was done then. Somebody had an idea. The SOSUS array, for example, which was a mainstay of the U.S. Navy Cold War defense, was done basically by a bunch of admirals going up to the Massachusetts Institute of Technology and saying, we need you to build us a concept for acoustic detection. It was sole sourced. By today's acquisition regulations, it was illegal. Somehow we need to turn around and allow some of that and have some new ways of getting public and private funds directed at these problems. That's why I'm convinced it will go up, because we'll define new ways of investing in these areas. You're starting to see it. The Chicago Climate Exchange, what's happening over here with respect to carbon markets, is a whole new way of funding some of these things. Some of those, I'd like to think that if I paid I can't remember what it was, 5.5 pounds or so for the flight over here from Virgin Atlantic to make my soul feel better for the carbon that we emitted. I'd like to think that some of that 5.5 pounds would go towards a research investment. That money's never been there before, so I think that's going to be fundamentally different. I think it's going to increase. It's got to increase once people recognize what the nature of these problems might be.